So last time we have developed a weak or variation formulation for at the example of the Poisson's equation with Dirichlet, with homogeneous Dirichlet boundary conditions. And one point where we made a first attempt, which was not yet feasible as we figured out, is to formulate a basic space, a basic vector space in which we look for the equation, for the solution of the equation. The first trial, what we did is we said, okay, we allow, roughly spoken, for kinks in the solution, so we only require that the solution is on some tessellation of the domain is only piecewise continuously differentiable. But we have seen that is not enough, because this space, at least in the norms which are, so to speak, the ones we have to use then, is not a complete space, it's not a Banach space. And you know, as we have seen, the variational equation is equivalent to a minimization problem. You can imagine that not every minimization problem on a non-complete space has a minimum. For example, if even if the functional has all the ingredients, so to speak, which are there to have a minimum. Take a parabola opened to the above, so of course we know there is a minimum, there's a unique minimum, but it's only on R, on the complete Banach space R, the real numbers. If we would say, okay, we shift the parabola such that square root of 2 is the minimum, and we look only at the minimization problem on Q, then we don't have a minimum. And that's the same situation we are now encountered with our space, that is, our space is not large enough. So another possibility would be to say, okay, we need first order derivatives. So let's just say we take functions which have first order derivatives, pointwise. Pointwise always means almost everywhere in the sense of the Lebesgue measure, without any requirements on what kind of functions those derivatives should be. But that's also not a good idea, because in real analysis there are some quite strange functions. For example, there's Cantor's function. You might have heard of it. Cantor's function is a function in the real, so on the interval 0, 1, and it has the properties, a continuous function. It is not zero, it's not constant, it is differentiable, and the derivative is 0 almost everywhere. But what does that mean? It just means that the Hauptsatz der Differential- und Integralrechnung, the basic theorem of the calculus of analysis, is not valid anymore, in the sense that we can regain in 1D the function as by integrating the derivative, because here the derivative is just 0. Here we could get a 0, but this function is not 0. But this is again the basis in 1D, and if it does not work in 1D, it cannot work in more than 1D. This is the basis again for partial integration. So we have no chance to do partial integration, and that was our starting point to derive the weak formulation. So this way is not feasible, so we need some requirements on those derivatives. And to do so, we need a new notion of derivative. And to develop that, let's first introduce a little bit of notation. The first thing is the so-called multi-index notation, which I'm going to introduce. So we have d variables, and we want to look at various partial derivatives in those d variables. And of course we can write it down in the way you might have used in analysis or in mathematics for engineers, or we can do it also a little bit more compact. Probably you did this more compact notation already. So what we do is the amount of derivatives we would like to have in the first, in the second, in the dth coordinate. So these are non-natural numbers. These are natural numbers, including 0. These we put together to a vector, and this vector we call multi-index. So this so to speak, the L1 norm of this vector we call the order or the length of alpha. This is the total amount of derivatives we would like to do. And then, on the basis of this notation, first of all, we can introduce a shorthand notation for polynomials, but not in one variable, but in d variables. The corresponding analog for a polynomial in one variable would be a linear combination of functions of this types, of products, of powers of the components. And this thing here we just write in a shorthand notation as x, the vector x, to the vector alpha. This is the shorthand notation for this quantity. And now we can transfer this shorthand notation for polynomials to differential operator as if we do the formal substitution in the sense that we substitute the vector formally by the vector of the partial derivatives. That means delta alpha of u means take alpha 1 derivatives in the first coordinate, alpha 2 in the second, and so on. So this is the notation we are going to use from now on. So now the important thing in the weak formulation we have derived was that we said we do not look anymore at an equation pointwise, but we more look at the reaction to testing with a function, to multiplying with a smooth function and integrating about that. And we can, of course, do the same thing now only with a derivative. This is, so to speak, a very special differential operator what we have here. And if we again use as a test functions the C infinity 0 functions, the compactly supported C infinity functions, what we can do is we can put here so first we start with a function which has this derivative in a classical sense. So we are looking at functions from ck of omega, and that means we have all the derivatives as continuous functions, maybe up to the last ones. So this notation means all the derivatives exist and are continuous functions. And so we have all those quantities here in a pointwise sense as a continuous functions. If alpha going up to the length up to the order of k. So what can we do now? Each of these partial derivatives, which is here, we can put over by partial integration to the test function phi. We don't have any problems with integrability because of the phi here, of the compact support of the phi. We are always on a compact subset of omega, having a continuous functions. That means we always deal with bounded functions there, so there's no question that all the functions which are involved here are integrable. So we bring all these derivatives over, and in each step we change the sign. So in total we change the sign k times. And boundary integrals do not appear because our test functions are all compactly supported, meaning that all their derivatives are compactly supported. All derivatives vanish at the boundary. Okay, so what we are doing is we're not looking at the derivative as a function, but we compose a functional out of the derivative. I do not fix the function spaces right now, and only look at the action, so to speak, of the derivative on such a test function. And we see we can express this in this form here. And you see, this now is a quantity which makes sense basically for every function u, for every locally integrable function u. There's no derivative on u anymore. So now we turn the thing around and say a function which represents, in the sense as the delta of u represents this functional given here. I have not yet specified spaces. This we call a weak derivative. So a weak derivative is a function of some regularity, and we only consider the situation where this function is an L2 function, which as a functional, and you know in L2 at least, you have this duality of L2 and this dual space, the Riesz representation theorem. Every continuous functional can be represented in a unique fashion by a functional of this type here. And this is now our new definition, saying we are looking at L2 functions, and we say that such an L2 function has a weak or a generalized derivative for this multi-index alpha. If for all test functions, if we call this if there is such a function v, also from L2, this is what we call the weak derivative, and this relation should hold true. The functional composed out of the v should be exactly the one which we would have got if we would have had the derivative. Okay. The first thing is to see that this notion is well defined. That means that we cannot have two different weak derivatives. Let's assume we have two of those things. We have a v1 and a v2. Then we subtract the whole thing. That's very similar to the argument we did for the uniqueness in the variational equation. So all the right-hand side, which is the same, cancels. And we get then an equation which says integral over v1 minus v2 for all test functions phi is 0. Now we have to know that this, and we discussed this already a little bit last time, that the space of test functions is dense in L2. That means for each L2 function, I find a sequence of those smooth functions such that the sequence of functions converges in the L2 sense to the function. The consequence, because this functional which I have here is a continuous functional on the L2 space. This is an L2 function, and therefore if I take this as an argument, that it's just the Riesz theorem tells me this is just the continuous function. Every continuous function can be represented in this way. But by continuity and by density, then I know that this holds true not only for the test function, but for all L2 functions. Now I'm allowed to take the difference. This is a L2 function. I was not allowed to take it here because the difference usually does not have this smoothness. Now I'm allowed to take the difference, and now I see, okay, I just get the L2 norm squared, and due to the definiteness of a norm in the sense of equivalency classes, as we have discussed this, we know v1 is equal to v2, of course, only almost everywhere, as we are dealing with measurable functions with L2 functions. Okay, so if a function has a weak solution a weak derivative of order alpha for multi-index alpha, in this sense, then the derivative is unique. And by the derivation, we have seen that those functions who have the derivatives classically, and I think that not even the bar is necessary. We could take omega. That's what I discussed because of the compact support of the test functions. In this case, I have to correct myself, and you have to tell me why I have to correct myself. In this situation, the classical derivatives are weak derivatives. Why do I really need this requirement, or not really need, but why is this why is more necessary than just ck of omega to fulfill the notion of weak solutions? Why I have put a bar here? I could have done it weaker, but why I cannot omit the bar? If I omit the bar, what does that mean? I know all the derivatives exist pointwise and they're continuous functions on an open set. That does not tell me anything how these functions behave globally, near to the boundary of this set. It does not tell me any integrability conditions. And here, in the definition of the weak derivative, I have two things. I have the fulfillment, let's say, of this special variational equation. This I have, as we have seen, but I only have to have that the function, which is then just the classical derivative, is an L2 function. And this property I would probably miss if I just say differentiable up to order k in the open domain. Of course, I could have also said, yes, but the classical function has to be an L2 function. That would be the exact requirement. So I can allow for singularities, but they have to be integrable. It's allowed that, yeah, okay, we had an example of this type last time. There was something with x to the alpha, alpha, big alpha in the interval, the open interval -1, 0, and so we had the integrability, and this was, in this sense, still okay. So the derivatives, and also, of course, the L2 function, as every L2 functions, they may have singularities, but of course, the square of the singularities has to be integrable. That's the notion of the space. Okay. So now on the basis of this new definition, and this new definition, maybe I make a remark, also I have no time for that. It has a lot to do with distributions. Who has heard this word already? Nobody? Nobody doing physics here? Have you heard of this fancy function of the delta function? Who has heard of the delta function? Okay, what is the delta? You can explain it to me. What is the delta function? Okay, go ahead. Yeah?
It's zero everywhere, but on one specific point.
Okay, let's draw a picture. It's a function which is what? Zero everywhere. So the specific point we take 0. Doesn't matter. Okay, here it is equal to 0. And what is it here? Infinity. Infinity is a fancy number, isn't it? Infinity, okay. And does it have further properties? Yeah?
It's integral as well.
And you really...
One.
Yes, you're really saying that without blushing, without being ashamed? Saying that you should, everybody of you should know that this is, of course, what is given there is mathematically rubbish. Okay? That's okay. Doesn't matter infinity. Okay, it's a fancy number. Let's say 5. But of course, this function, the integral is 0. In any reasonable notion of integration, this integral is 0, of course. That's a very, very tiny set of measures 0 here. So what does that mean? Not that what you told me, and not what the physicists say. I'm not saying that the physicists not really know what is really behind it, but that is obviously this is rubbish. So what is meant? What is meant, let's call this function maybe now delta 0, what is meant is that I have a functional delta 0, a functional on some function space W, which I do not specify. So a linear continuous functional. And what should be the property of this functional? So where do you use this here? You use this property when you say, okay, I want to do something like that. Delta 0, x minus y, fy, and this gives me by some magic, which has nothing to do with mathematics, f of x. That is how it appears in these computations with point sources or whatsoever. But what is really meant is that you have a functional, and we speak now, so to speak, about this guy here. And what does it do? It does exactly what it's saying here. It says that this functional, if it is applied to some function from W, which I not have specified, it just takes the value at x of this function. So this is this is just an evaluation functional which you have seen already dealing with function space. It's an element of the dual space, of the algebraic dual, and now the question is really to make this rigorous. It should not be an element of the algebraic dual, but also of the topological dual. And that means we have to have, first of all, we have to have here the right space. We would like to have something like our test functions here. We can relax this a little bit. We can relax the compact support. We can allow, but we have to have certain degrees conditions at infinity. So this would be the test function. And then we have to have a topology that everything is okay. And there the things becomes difficult. This cannot be done as a normed space. You need a so-called locally convex space. It is something you should, maybe in a second course in functional analysis, you may hear about that. But if you do this, if you define a distribution then is just an element phi from this dual space of omega, of W, which I do not have specified. The point is that W is something like, I said, let's say this one. So the point is, what we can now do, we can define derivatives of distributions. How would you define this guy here? Maybe f is not a good notation. So let's go back, and let's say what I called here f is the phi there. So how would you define this one here? Looking at this line here. What did we do? We put all the derivatives correspondingly to the test functions. Do the same thing here. What would be the definition? Minus 1 to the k. So k is the length of alpha, phi of the derivative of the test function. This makes sense here with our space. So what do we do here? So what is the procedure here? What do? We take our function u. We make, so to speak, a distribution out of this function, or we see this function in a distributional sense, as is also said. That means we do not consider the function, we consider the corresponding induced functional, integral over u times phi for the test functions phi. For this distribution, we take the derivative in the distributional sense, meaning putting all the derivatives to the test functions. And then we require, this is not just a weird distribution, it's not the delta function, it's again a function, an L2 function. That does not happen with all functions, of course. For example, this function here. Let's call this function, this is the u. What would be the u prime in the sense we have just introduced? What do you think? What would be the u prime in this sense? What do you think? What does it mean? You have to find a function v, such that the function v multiplied with all those test functions exactly gives this quantity. Okay, this quantity is pretty simple. The derivative, what is the derivative? The derivative is here 1, and here minus 1, and here it is not defined. So I have here this function, I have this function here, and this L2 function is just my weak derivative. It's an L2 function, obviously, what I have here. And here I say it's not defined because I don't have to define it on a set of measures 0, or it's this value, or it's this value, or this, doesn't matter. It's a set of measures 0. Okay. Let's go on. Let's find the derivative of this function here. What is the derivative of this function? Now, doesn't work. We cannot find an L2 function. What do we have? We have, if we do it pointwise, we get 0. But the 0 functional is not really what we want to have. So what would be the derivative? It would be, delta 0. It would be, in the way I sketched it, the delta distribution. Okay, so that's, I cannot go too much into details here, but maybe it's helpful to know these words and you can look it up. So what we are doing here, we're taking L2 function, taking the distributional derivative, and require that those distributional derivatives are again functions in the L2 sense. That is the key thing. Okay, so, and on basis of that, we now can define the appropriate real correct vector space, and this is the so-called H1 space, H1 of omega. That's the first and simple so-called Sobolev space, and we do exactly what we said. We require that the function is L2, and it has weak derivatives, all weak derivatives, first-order weak derivatives for all the components 1 to d, and all should be in L2. So now we can define, on the H1 space, we can define a scalar product consisting of the scalar product of the L2 scalar product, so to speak, dealing with the zeroth order derivative. And with the first order derivatives, we do the same thing. They are L2 functions. And this scalar product now gets the notation 1 because we have derivatives up to first order. And that maybe explains why I used the notation 0 for the L2 space. So this scalar product induces a norm. And the norm consists of a part dealing with the L2 norm of the function. This we have seen already. And a part dealing with the L2 norm of the gradient. This we have seen also already. That was our A norm in our example. So everything very fine up till now. There's one tiny problem left, namely what do we do with the boundary conditions? And we have seen that we have to include the boundary conditions into the space in the sense that we have to require that all functions, all possible solutions, all test functions have to be 0 at the boundary. Okay. This is in 1D, this is not so problematic, but from 2D on, the problem is that there are unbounded elements of the H1 of omega. So we cannot speak in a naive, pointwise evaluation sense of what U should be at the boundary. In the sense of the d-dimensional Lebesgue measure, the boundary of our domains, if you think at these standard domains we have in mind, and we will later require certain smoothness of the boundary, in all these cases, the boundary is a set of measure 0. It's a d minus 1-dimensional set. In the sense of the d-dimensional measure, it just does not exist. So to say, it doesn't make sense for an L2 function to say, I require that this L2 function is 0 on the boundary. So we have to have, but we have, of course, more than an L2 function. We have H1 functions. And on the basis of that, we need a proper notion of what it means to evaluate a function at a boundary. That is the so-called trace of the function. So we have to define the trace of the function, of an H1 function. And then we would require that the trace is 0 on the boundary. And that gives us the subspace H1 0. So this is something we still have to do. In this sense, we are still not yet finished with the definition of the proper space. So if you feel more comfortable, you can also go to this first preliminary definition, which means that we are dealing with a non-complete space where we in general have no solution of the continuous problem, but for the discretization, at least for the setup of the discretization, it's enough. And that's what we want to do now. Now we want to discuss what finite element methods are. Okay, so what is the situation we have in general? We have a vector space, we have a bilinear form A, we have a linear form B. We're looking for a solution of the variational equation, AUV equals BV for all V from capital V, or under the assumptions we have seen, equivalently for a solution of this quadratic minimization problem. And we have seen conditions which have shown us that these two problems are equivalent. So what we do now, there are now two possibilities what we could do. So of course we can never solve such a problem with, so to speak, infinite degrees of freedom exactly. The only thing at the end of the day what we can solve is a set of equations, maybe even with 10 to the 6 unknowns or 10 to the 10 if you're more ambitious, but still a finite number. So we have to make a finite dimensional problem out of that. And those two things now suggest two ways. Let's start with the second version here. Okay, we want to minimize on a very, very large space. This we cannot do. Maybe we can minimize on a finite dimensional subspace, which hopefully is a good approximation of this very large space. So what we do is we choose a finite dimensional subspace VH. So now all the finite dimensional things, they get the index h. So numerics is very simple. You put an h to everything and that's it, in principle. Okay, now we say on this finite dimension, we will later see what this h really means in finite elements. On this finite dimensional space VH, we just say, okay, now we solve the minimization problem, but only on this finite dimensional space. Of course, this really requires that we are able to evaluate this functional on all elements of the finite dimensional space. But we will later work this out, how this problem looks like, but it's then a finite dimensional quadratic minimization problem which comes out. The other possibility, this would be the so-called Ritz procedure. The other possibility, which is a Galerkin procedure, would say, okay, we look at the variational equation and we try to solve the variational equation in this finite dimensional space. And now we have to put as many as requirements in terms of the dimension of this space to this solution we are looking for. That is, we have now to allow for all the test functions from this finite dimensional space. This formulation will turn out to be just a set of equations. So this is what's called Galerkin. These are pretty old ways to do so, and the finite element method is then a very specific choice of the Ansatz space. So this VH is also called the Ansatz space, and which then does not only lead to a set of equations. This is if you would have any set of equations and say, okay, now I have 10 to the 6 degrees of freedom. I'm not sure whether one can do something right now with the existing algorithms and with the existing computers. But what will turn out, what is specific and important and necessary for the finite element method, that the set of equations which come out, they are sparse. They have not very many entries in the matrix. They have matrices which are similar to the matrix we have seen already in the finite difference case. Okay, so now let's define the space. Now we become specific, so we are in 2 dimensions. We take this preliminary definition, or the WH1 of omega, not really knowing what the equal to 0 at the boundary means. We go to our special situation with a Poisson equation. And the domain we are looking at, we assume that it's polygonally bounded. That is, that we have a set of straight lines, the union of which is just the boundary of the domain. This simplifies a lot. It's not really necessary. We can do also something for curved boundaries, but this we will do later on. So the basis for the definition of our space is a tessellation, a triangulation of the corresponding set omega. And what we do is we tessellate omega, or more precisely omega bar, the closure of omega, in closed triangles. So if I denote here a triangle, I always mean the closed versions, including the edges. What are the requirements? The union of all the triangles should be identical with the closure of omega. This still allows that those triangles overlap. This we don't want to have. So this is the next requirement. We want to have that the intersection, if I have 2 triangles and I look only at the interior of the triangle, so omitting the edges, then the intersection should be 0. Or say it in other words, the triangles can only intersect at edges, at vertices, or at edges or at vertices. Okay, let's have a look at a picture. What I said up till now, that would be satisfied in this case here. So we have triangles. The union of the closed triangles is this rectangular domain. And the intersection of the triangles only consists, what did I say? I said that the interior triangles have nothing in common, and that's also the case here. And if we look at now a little bit more close and look at the intersection, then for example these 2 triangles, the intersection of these 2 triangles is just one common edge here. If I look at the intersection, let's say, of this triangle here and this triangle here, then the intersection is just this vertex here. These are things I would like to allow. There's one thing I don't want to allow, and this is this situation here. I don't want to have that a vertex from the one hand side, so to speak, lands in the middle of an edge. So I don't want to allow that an edge from one triangle is only a part of an edge of another triangle. There are also methods which can deal with this kind of triangulation. This would then be called a non-conformal triangulation. But in the classical finite element method, we omit this. We only allow for conformal triangulations in the sense that they have to look like this here, in the sense that if two triangles have one edge in common, then it must really be the full edge and not only a part of it. And this we can formalize in this requirement. If two triangles have a non-empty intersection, then the intersection is either a point or a common edge of both of the triangles. So this is a conformal triangulation. And this conformal triangulation will be the basis of the definition of our finite element space. So finite elements have different ingredients. The one is this geometrical aspect. In a more narrow sense, one also calls these triangles or other geometric quantities we will see later on, we'll call this then elements. But a finite element is more than just this triangle. It also needs a certain Ansatzspace that's to compose this finite dimensional space out of on the basis of this triangulation, and it needs degrees of freedom. We will later see this more precisely. So if you look at the 1D situation, in the 1D situation it's quite simple. In the 1D situation I have not so many domains in the 1D situation. Basically they look like that. And what are the triangulations in the 1D situation? I cannot triangulate in triangles, of course. I have to triangulate in intervals. How do I get a triangulation, a conformal triangulation in the sense now substituting triangles by intervals? What do I have to do? I just divide in small subintervals. And this you see what makes a little bit of problem in the two-dimensional case, and maybe a little bit more in the three-dimensional case, we don't see here in the one-dimensional case. So what we do is we have those triangles, we number them from 1 to capital N. And now we will later see the more triangles we have, or the smaller the triangles, I should better say the smaller the triangles are that we have, the better the approximation in some sense will be. So we will use as an indicator for, not an indicator, that's a misabuse of a word which has another meaning, as an indication for what we are doing. We define as h, as index h, the fineness of the triangulation, meaning just the maximal diameter of the triangles. So the h, of course, again corresponds now to the h in the finite difference sense. In the finite difference sense, maybe we should have this also in mind. If we have the finite difference sense, maybe not so big, then we had those grid points, and how can we relate this to a triangulation? Okay, we can say, we make a triangulation which has exactly those grid points as the vertices of the geometrical objects. And that would be the first choice, but now I said we would like to look at triangles, not at quadrilaterals. Later on we will also look at quadrilaterals. How do I make triangles out of that? What would you suggest? What shall I do? Okay, I have basically two choices. You can do this one, for example. Okay. This is a very special way in triangulate a rectangle into triangles. That is what we later will call the Friedrichs-Keller triangulation. You can, of course, do it also the other way around. Doesn't matter. Doesn't change the discretization. As we will see, at least not for this specific equation we have. Oops, should not be, of course, not. Okay, so now I have triangles. Okay, so and now you see again the h. This is for each triangle. We don't have the maxima; it's always the same quantity. This is exactly the h what we had before. So these things relate to each other. So, okay. So now the triangles, of course, have nodes. They have vertices. We call them nodes. And the total set of nodes, they get some numbering, at the moment arbitrarily, only with one condition, just to facilitate a little bit the notation. We first number the nodes which are in omega, and then we number the nodes which are at the boundary. And we use, as you see, exactly the same notation we have used for the finite difference method. M1 for the number of nodes, for the grid points in the interior, and the rest for those at the boundary. Here you see it. So we have our elements. We number them somehow. So we have here 12 elements, 12 triangles. We have here 3 nodes in the interior. 1, 2, 3, and all the other ones. So this would be M1 equals to 3, and all the other ones are at the boundary. This would mean M2 equals to 8 and M equals to 11. Okay, and now what is the reasonable ansatz space we would like to use? And I first show it to you in 1D. The ansatz space we would like to use would say, okay, it depends. It consists of 2 things. The one thing is a local smoothness requirement. This would say on each of this would, so to speak, my element ki. And what I would like to have is I would like to have on the element ki, it should be a polynomial of first degree. Of first degree. That is the first requirement, a local requirement. The global requirement is that the function, the total function which comes up, should be a continuous function. So I'm not allowed to jump here. Also those kinds of spaces exist. I'm not allowed to jump here, but I have to continue here in a continuous fashion. And then, of course, I want to have my boundary condition. That means I have to go here to the 0. So what I have in 1D, it is just a continuous polygon. It's an element of, you might have called it S1 of delta, of the continuous linear splines. So what we are doing is, in some sense, it's a sort of a generalization of the spline functions, what we are doing. So what do we require? We want to have that the functions are P1 functions on each of the triangles, a polynomial of first degree. First degree means they are of the type alpha plus beta x plus gamma y. So this indicates that we have a local 3-dimensional space. Here we had a local 2-dimensional space. And this is the one requirement. The other requirement is we want to have a continuous function on the closed domain. And furthermore, we want to have the boundary conditions. And the question, so first for the notation, so we will use P1 of k or P whatever, L of k for the set of polynomials of degree L. Degree means is to be measured in the sense of this multi-index notation. So degree means the length of the multi-index. So here we have to have all multi-indices of length 1. So this has length 0 up to 1. This has 0. This is 1, 0 has length 1. This has 0, 1 has length 1. xy is already a term of second order. So this would appear in P2. P2 would have the 1, so the constant, x and y, what we have, xy, x square, y square. And so on for higher degrees and correspondingly then in d dimensions. Okay. So what we only need is this, that they are polynomials on this triangle, but we are a little bit sloppy, not in the sense that if we have defined a function to be a polynomial on a triangle or on a set which has an open set, let's say, then of course it also defines in a unique fashion a polynomial on the whole space, because polynomials only have a finite set of zeros, so it doesn't matter so much to indicate here the domain of definition. So the point is we have to check what we want to have in general. That was the notation, one of the basic ingredients of our either Galerkin or Ritz approach. We want to have an ansatz space, a finite dimensional ansatz space, which is in our basic space. So we have to check this, that is here the case. So, and that is basically the reason why I have chosen this preliminary non-correct definition of the space V, because here it's very easy to check. Because now we are exactly in the situation which underlies the definition, this preliminary definition. We have such a desolation of omega by the triangulation, and we have derivatives on each of those open sets. The open sets would be the open triangles. Polynomials of degree 1 have constant partial derivatives, and of course these constant functions can be extended up to the boundary. In general, they will not form a continuous function. So in what we have, so to speak, the two-dimensional analog of this mountain range here. We have pyramidal structures of planes coming together, but coming together in a continuous fashion. Okay, for the new correct definition, it's not really clear, but it's clear what we have to do. What we have to do is we have to take those piecewise defined functions, defined as, in our case, a polynomials of degree 1, have, so to speak, guess the weak derivative. This should be an L2 function, of course. And then we really have to show that this is, by the definition, have to show that this is the weak derivative. Yeah, what is the candidate for the weak derivative? How would you put up, so to speak, for example, the first partial derivative? What is a possible candidate? What could you do? We know in the situation where everything is smooth, then the notions should coincide. So the only possibility what we have is to take, in the interior of the triangle, to take the partial derivatives which we have. This defines us a piecewise constant function. And what we then really have to show is that this piecewise constant function is the weak derivative in the sense we depicted. And for that, again, to show that, we need, and this actually is equivalent, that the function is continuous. So this continuity requirement in the ansatz space is necessary to have this property here for the ansatz space, to have a conformal discretization. We could also we could make our lives simpler and say, who cares what happens here? We could say, okay, I'm fine with this function, piecewise linear. It's much easier to handle. But this function is not in our space V. Then we have to make another. Methods of this type also exist. The so-called, which is now quite modern, the so-called DG methods, discontinuous Galerkin methods, are of this type, but they have a totally different theory. Okay. what we would now like to see is what is sort of obvious here. What is sort of obvious here, let's look at the one-dimensional situation. It is pretty obvious, and I hope at least you have shown this already once. For this space here, for this continuous linear splines, the interpolation problem is uniquely solvable. What do I mean? I mean I specify any values here, and then of course there exists a unique polygon going through. And when the value I've specified at the boundary is 0, also such a thing exists, and the boundary condition is fulfilled. Because here, in the one-dimensional situation, I have the identity, so to speak, of the boundary set and the corresponding vertices of corresponding nodes of the interpolation problem. In the two-dimensional, higher dimensional situation, it's a little bit different. So what we would like to have is, we specify values at the nodal points, so at all the edges of the triangle, and there exists uniquely a function of the space VH we have just defined, this continuous piecewise linear functions, which go through these values, which is a solution of the corresponding interpolation problem. In addition, we want to have, if we specify the nodal points at the boundary points to be 0, this function which comes out is not only 0 at the nodal points, but at the whole boundary. That we fulfill then by this the boundary condition, exactly, the 0 boundary condition. In this sense, we would like to see that the values at the nodal points are the degrees of freedom of our ansatz space. So we have what is more or less obvious in the one-dimensional case, we have to prove now in the two-dimensional case. And what I would like to do is I will do a very complicated, unnecessarily complicated proof. But the reason for doing so is that this proof is as it stands, we can then transfer it to more general situations. So we will see the general arguments in these very simple situations. So let's start with a little bit of a larger space, not VH, but XH. It's defined exactly in the same fashion, but we have omitted here the requirements at the boundary. So there are any values at the boundary here. So, and the assertion is, in this space, the interpolation problem is uniquely solvable. That means I give any values u1 to um, and then there exists a unique element u of xh that a at the nodal points ai equals to ui. And the further assertion regarding the boundary conditions is, if I choose the values to be 0 at the nodal points, then this function which comes out is not only in xh, but in vh, meaning it's 0 at the whole boundary. So let's prove this. And what we will do is we will, so to speak, we will rely on corresponding results in the one-dimensional case. And the only thing what we need in the one-dimensional case is, so to speak, the interpolation problem for the linears. For P1 in one-dimensional, through 2 points, there is a straight line. There's a unique straight line. That's all what we need. And that, of course, means, in particular, if the values we require are to be 0, then the straight line is the 0. That's all what we will rely on. So what we do is we first start with a local interpolation problem. So we look only at one specific triangle, and we ask ourselves, is there a P1 function such that PAI equals UI? I've now taken here a local notation, so I have just denoted these 3 vertices, these 3 nodal points with 1, 2, 3. That's, of course, also something which we know from elementary geometry. Through 3 points, there is a unique plane, of course. But let's prove this and in a way as I indicated. So the first thing is what we do is we look at a very special triangle, a so-called reference element. That's this triangle K hat. It has these three vertices here, 0, 0, 1, 0, and 0, 1. And at this very special triangle, we can, so to speak, solve the interpolation problem explicitly. So the assertion is the solution for the solution for the interpolation problem is this linear combination of three specific functions, n1, n2, and 3. They are called shape functions then in the finite element terminology. And you see there are not any coefficients which appear here in the linear combination. It's just the values we want to interpolate. So let's look at these functions. Why we have chosen exactly those three functions? And you see, if you look closely, these three functions have the property, and you know this property also from, for example, if you in 1D, if you know the so-called, how are they called? Lagrange basis polynomials for the one-dimensional polynomial space. They have exactly the same situation. They have the property that the one with the index I is 1 at the nodal point with the index I, and it's 0 at the others. Let's check this, for example, this n1 x1. That is supposed to be 1 at point 1. Point 1 has the coordinate 0, 0. That's okay. And for the other 2 points are 0, 1 or 1, 0. Then we subtract here a 1 in both cases, and we get 0. And the other two is the same thing. So, okay. Now, what we have here is a P1 function, because it's a linear combination of P1 functions. This is a vector space. And it's really a P1 function which fulfills the interpolation property. We just have to check that. Because if we plug in here, okay, so this is now the assertion. The assertion is that this linear combination, on the one hand side, if we evaluate this at the three nodal points, we get exactly the three values. Why is this? If I plug in one of the nodal points, let's say the first one, then I get here a 1. So I get u1, what I would like to have. But here I get zeros, so my u1 is not disturbed. And the same thing with the other two. So this is a interpolating function. But it's also the unique interpolating function, because assume we would have two interpolating functions. Then we subtract them, and we get a new element of P1, which now interpolates the zeros at those three nodal points. Is this possible? In one dimension, it's not possible. But that is not possible. It's just a restatement of the uniqueness. So what do? So our difference function has this general form as every P1 function. So we look at one of the edges, choose y equal to 0. Then we get a polynomial in x, interpolating 0 and 0, and therefore this polynomial has to be 0. So we know alpha and beta must be 0. Okay, alpha is already 0. Now we take another edge, for example, x equal to 0, then we get this form of the polynomial. You have the same situation, a polynomial first order in one variable interpolating at 2 points. The 0 must be 0, so also the gamma is 0. Actually, this proof was not necessary, because what we have here, that what we discussed last time, when we are here in a finite dimensional space, we require as many, what is reasonable, of course, and also necessary, we require as many conditions as we have degrees of freedom, as we have dimensions in the space. We have a three-dimensional space. P1 is a three-dimensional space, and we have three requirements. That means our interpolation problem is just the question, is a quadratic set of equations uniquely solvable. And we have reminded us that in this case of a quadratic set of linear equations, injectivity equals surjectivity. So we have to check either solvability or uniqueness. One is sufficient. The other is always a consequence of it. When we have solvability, then there has to be uniqueness, or the other way around. So that is an argument we will do later on, and here we have done a little bit too much. Now, what do we do with a general triangle? A general triangle, maybe you know this from affine geometry, can be bijectively mapped by an affine mapping. So a mapping of the form linear mapping, that means matrix times x hat plus a constant part, can map by an affine mapping to the general triangle. And the only thing what we have to require is that the nodal points are mapped to each other. And because of this, now I use a little bit of notation from affine geometry, as the edges are convex combinations of the nodal points, of two nodal points, and all points are convex combinations of the three nodal points. This is a consequence that correspondingly the edges are mapped to the edges and the full triangle is mapped to the triangle. So that is the only requirement we have to fulfill, but that these three conditions gives us our three vectors we have in the problems, namely the D and the two columns of the B. Because if we plug in the x1 hat, so the 0, we see the D must be A1. And if we plug in the A2 hat and the A3 hat, we get these relations here, and this gives us that necessarily the two columns here must be the connecting vector from A1 to A3. So A3 minus A1 and correspondingly here. And as we have, now is this matrix regular? Yes, it is, because these two vectors are linear independent. Just means we have a triangle and not all the 3 points on a straight line. So we have affine linear independence of the 3 points of the triangle. Okay. So that is what I said already. So in general, the triangle is the convex combinations of its three edges. That's the same thing for the, of course, for the reference triangle, and an affine mapping just transfers convex combinations to convex combinations. So we get this bijective mapping for the whole triangle and also for the edges. Okay, so this would be the picture for that. And that is also a decisive ingredient of a finite element code, because that is what we are doing. When we, in the end, set up our set of equations, we have to compute integrals over triangles. And we do so by transforming those triangles back to the reference triangle, to the reference element. So, because of this bijective mapping, of course, we also have the unique solvability of the local interpolation problem on a general triangle. Because the affine mapping is also P1 mapping, so we do not, by this transformation, we do not change the P1 property. So now we have to glue these local solutions together. And what should come out is a continuous function. And the only thing what we know is that the function, so to speak, is continuous in the vertices, in the nodal points, because there we have required the same value corresponding. So what is the situation now? We have maybe 5 elements, or not so many. Oops. We have here several elements which come together in one point. In this point, we have for sure they have the same value. That's the interpolation property. And the same is here, and the same is here. But what we do not yet know is that they have the same value on all these edges. So we do not yet know that they're really continuous. How can we argue to show that they are continuous? Okay, so we just take two of those elements which have a common edge. So we have here a k with k, a k prime have a common edge e. So, so what does that mean? Here we have a two-dimensional polynomial first degree, here also. On this edge, we gain now a one-dimensional function, also of first degree, polynomial first degree. To see this more clearly, we can again do the affine transformation and just transform the element in such a way that this edge, which lies somewhere, just becomes the interval 0, 1. And now we really see, okay, here this is now a linear function, a P1 function in the one in the x variable. We have here we have the same values here and here. So therefore we have to have the same values here on the whole line, because we get, so to speak, the same interpolation problem from the one triangle and from the other, leading to the same function on the whole boundary. Okay, so just by gluing together those parts, we get a continuous function. And as that is a solution of the global interpolation problem, it's also a unique solution, because any solution also produces solutions of the local problem. The local was already unique. So what is now still missing is to see this thing with the boundary conditions. So we are here now at the boundary. Let's say this is the boundary. This whole omega, so we only have 1 degree of freedom actually in the problem. It's not very much. So here the boundary, we have it now always the 0 values. What we would like to see that also at all those parts of the boundary, the solution really is 0. And that's the same argument we had before. We do the same affine transformation. We look at this straight line. We know now we have an interpolation problem. In P1, both values are 0, then the whole solution must be 0. Okay, that's it. The nice thing is that we now have, because of this unique solvability of the interpolation problem globally, the only thing is to deal with such a function of xh or of vh, the only thing is what we have to do is we have to say what this function is at the nodal points, at the degrees of freedom. Then it's uniquely defined. That's what we have shown. So for example, I can do the following. I can say I would like to have those functions which have the following property. I denote them with phi I, and they should be 1 at the nodal point ai and 0 at all the others. So what I had with the shape functions locally, so what are the shape, maybe again, so this is, so to speak, then the reference element. This is k hat in the one-dimensional case. And what how do the shape functions look like here? So the one which is 1 here and 0 here is this one, and the one which is 0 here and 1 here is this one here. And you see, these are, so to speak, the building stones with which I build together this kind of function. And the same is now in the two-dimensional, or then later on d-dimensional case. And now we see how this function looks like. This is, so to speak, okay, we will discuss this later on. So these are very helpful functions. They are uniquely defined. They're in xh. And first of all, and if I, so to speak, omit in my collection here, I omit the exterior points, the points at the boundary, then I get a function in VH. So what does that mean? And this is exactly the same argument we did already for the shape functions. Because of this property, this nodal property, also called nodal basis functions here, because of this nodal property, we get this relation. So we now know immediately what is the solution of the interpolation problem, namely that is this guy here. So if I specify values, so I can see it from two sides. Either I say I have any function in xh, then I can represent in a unique fashion this function by those functions vi, telling me that these vi are a basis of the space. And what do I have to take as coefficients? I just take the values here. We have to check that this, how do we check that these two functions are the same? How do we check that? What do we have to check to prove that these two functions are the same? How can we now use this knowledge about the interpolation problem? They are both elements of xh. They are the same if they are the same if and only if they are the same at the nodal points, because of the uniqueness of the interpolation problem. So we check what is this at the nodal point, ai? This is obviously uai. And what is this at the nodal point? It's also uai, because all the others contribute 0, and for the corresponding index I get a 1 here. So I get this representation. This tells me I can show it as a linear combination, but only in one way. So I have a basis. And, okay, the nodal basis. These functions, they are also called pyramidal functions. Why is this? This is, I will not draw it now. But let's say this is ai here, this nodal point. So we are now, this is only a part of the omega now. It goes on here, doesn't matter. So how do they look like? How do the phi I look like? It's 1 here, and it's 0 in all the other nodal points. For example, if we look at this triangle here, which is, so to speak, away from here in the sense this ai is not a vertex of this triangle. What is phi I at this triangle here? 0. Uniqueness of the interpolation problem. What is this on this triangle? It's a plane which has a 0 here, a 1 here, it has a 1 here, a 0 here, and a 0 here, and corresponding those. So it's a generalized pyramid shape, what we get here. Okay. And again, what I said already, if we take the sum only, so if we omit, so to speak, the degrees of freedom which lie on the boundary, that means we only have basis functions which are 0 on the boundary, and therefore 0 at the boundary nodal points, and therefore on the whole boundary, as we have seen, then we get a basis then correspondingly of the space VH with a zero Dirichlet boundary condition. And you see the dimensions, they all correspond. Sum of all the nodal points, sum of the interior nodal points. Okay, so let's put it together. What we have shown if we the values in the space xh or correspondingly in the space vh with a zero Dirichlet boundary condition, the values at the nodal points are exactly the quantities which determine uniquely the function, and therefore we call them the degrees of freedom. Okay, and if we have additionally the zero Dirichlet boundary conditions, then only our interior nodal points are or have the degrees of freedom. So without now going in the general definition, we can already have a look forward. So what is a finite element method? A finite element method consists of a triangulation of the domain in certain simple geometrical objects. And then a local finite element consists of three things. The one thing is this specific object, triangle or whatsoever. Then the local ansatz space, in our situation the P1. And in addition, that's not enough yet right now. And in addition, the position or the functionals which describe the degrees of freedom. So at the moment, our functionals are just evaluations of the corresponding function. We take values of the function at the nodal points. What we could also have done, we could have said, okay, this is our triangle. We take triangles. We take P1, and we take our degrees of freedom here. This is also a possible choice. This is our so-called Croisset-Raviat finite elements. Can you imagine what the problem is, what comes up here? You require that planes come together only in this point. You see what is possible? Those functions will not be globally continuous in general. So this is outside of our theory. So there's always the three things. Geometric element, ansatz space, degrees of freedom. So, okay, let's make it a little bit more concrete and just see what kind of work we have to do if we now want to compute this approximation. We do not know how good this approximation is, but let's first compute it. So, and we can do this consideration quite general. So we look first at the Gajerkin method. So we have any basis, phi I. We can have this nodal basis in mind, but this doesn't matter here for the consideration. We have any basis of the ansatz space, meaning that any function, including, of course, the solution, can be represented in a unique fashion, and computing the vector of the xi's means computing of the UH. And you really see the difference to the finite difference method. In the finite difference method, we had values at the grid points. We had no idea what would be a solution in between. The method did not give us something like that. We could interpolate and see how good this interpolation is. Here the method gives us directly an approximating functions, not only approximating values, but really an approximating function. So, okay, so this quantity we are looking for, that means we are looking for this vector psi. Now we have to allow here in the bilinear, in the variation formulation for all test functions from VH. Because of the linearity of the B and of the A in the second component, this is equivalent of taking there just the basis functions. Because having this equality for the basis functions, I also have it for every linear combination. And then we really see what this means. We not have an infinite amount of equations to be fulfilled. We just have m equations, as many as the degree of freedom tells us, as the dimension of the space tells us. So for the UH, we now plug in this representation. We use now the linearity in the first component of the A, and we end up with this formulation here. And you see what we have here is just a quadratic set of equations. The unknown is the vector psi. The matrix entries, this is the ijth matrix entries, is A phi j phi I. So note the transpose in the ordering. Of course, in our example, A is symmetric. It doesn't play a role, but for more general example, it plays a role. And the right-hand side comes from the evaluation of the linear form B on the right-hand side at the phi I. So what do we have to do that? First of all, of course, we have to put up this set of equations. That is what is called the assembly phase, or the assembly of the problem. So that means we just have to compute this right-hand side. We know already this has something to do with the computation of integrals. It might be possible exactly or not. And we have to compute the entries here of the matrix. This has also to do with the computation of integrals. And after doing so, of course, we have to solve the set of equations. That's all. And what do we do in the Ritz method? Yeah, we do exactly the same thing. And if we do exactly the same computation which I did on the other transparency, I end up with a quadratic functional to be minimized, now also in a vector eta, of exactly the same form, with the matrix AH here, exactly the matrix I defined before. By the way, this matrix is also often called the stiffness matrix, and the right-hand side the load vector, Steifigkeitsmatrix, Last vector, because this is a notation which comes from mechanical applications. Okay, you see here a quadratic minimization problem, and you may know that this, again, this quadratic problem here is equivalent to a set of equations in the case if AH is a positive, symmetric positive matrix, namely to this set of equations. So what we know already, or we can find here again, namely that those two problems are equivalent. Ritz and Galerkin are equivalent for a general space. Of course, they're then also equivalent for a specific finite dimensional space. So Ritz and Galerkin are under our assumptions, under more general assumptions different, but under our assumptions, they just lead to the same thing, and it just reflects or gives us again, or if you don't know, it tells us now this fact that solving the set of equations is the same thing as solving this quadratic minimization problem. And this, as I said already, I hope you know this from numerics, is the basis for the gradient methods, and in particular for the conjugate gradient methods, which is more or less the working horse here then. Okay, let's see what we have to do. In our special case, the matrix entries are of this type here. They are integrals, so we have to look at our bilinear form. That means integral over gradient of what? Of the basis functions. So we have to compute those gradients of the basis functions, set up this integrand, compute this integral. And the same applies for the right-hand side. And here we might get some problems, because if the f is a general function, we might very well end up with an integral which we cannot specify explicitly. So there we have to do something. But how to set up these quantities, how to compute this integral, that is what we then look at the next time. And we then will see what are the relations also for this special case to the finite difference method. So let's end here then for today.